Okay, so let me start. So we are discussing stability, power system stability, and uh, particularly this one. Oh, yes. So we have started equilibrium criterion in our previous class. What we have assumed the generator was delivering power to infinite bus to a large power system, and we have applied a fault to the terminal of a generator, and we have seen how we can explain the stability of the generator, or we can explain the increase in speed and decrease in speed of the generator, okay, using the concept of stored energy and released energy from the generator. Okay, so when the circuit breaker was closed and the circuit breaker was connected at the terminal of the generator, so when the circuit breaker is closed, it means that it is short circuited. At the terminal of the generator, a short circuit fault has happened. Okay, because of the short circuit fault, power output becomes zero instantly. Initially, this much was the power being delivered by the generator, and this was the operating point. As soon as the circuit breaker is closed, output becomes zero, and we have assumed that after some time the circuit breaker is opened again. Okay, so during this time when the circuit breaker was closed, speed of generator increased because input power was greater than the output power. As a result, power angle has changed from delta 0 to delta 1. It had increased from delta 0 to delta 1, and an area A1 is uh, available here. This area A1 represents an energy, and this energy is actually inserted into the rotor of the generator. From the external, from the mechanical power is being delivered, but output power becomes zero. So what happens? This power, obviously, it will be stored at the in the form of kinetic energy of the rotor. So rotor speed increases, delta increases. As a result, at delta equal to delta 1, what we have done again, we have opened the circuit breaker. So at delta equal to delta 1, this becomes the operating point when the circuit breaker is open, and at this point, obviously speed will be above synchronous. Now output becomes greater than input. So what will happen? Obviously, since the output is greater than input, speed will decrease from the value it has already achieved. Okay, the rotor has achieved a certain speed, and which is above synchronous. From that speed, it is now decreasing, but still it is greater than synchronous. So as a result, delta will go on increasing. As delta is increasing, you see that we can find an area A2 here, which implies the energy, which basically represents the energy that has been extracted from the generator. Why this has been extracted from the generator? Because generator rotor is actually losing speed. Its speed is being decreased. As a result, kinetic energy is released by the generator. This kinetic energy is actually being used to supply the power output. Okay. So here we assume that again the synchronous speed has been achieved. When the synchronous speed will be achieved? When A1 is equal to A2. Why? Because A1 represents the energy inserted into the generator. A1 represents the energy input to the rotor of the generator. A2 represents the energy extracted from the generator. Now, what is this energy? Obviously, this A2 represents the energy that was extra, that was above the energy stored during the synchronous speed. Okay, and how much that energy actually was? It was energy given by this area A1. We assume that here again the speed is synchronous. So speed is synchronous here, it is above synchronous here, it is synchronous at this point. Since we are talking about the kinetic energy stored in the rotor of the generator, and since the generator rotor is rotating at synchronous speed here at delta equal to delta 2, then the stored kinetic energy here will be equal to the stored kinetic energy here. This implies that area A1 has to be equal to area A2. And hence the name comes the equal area criterion. That means two such areas must be available for the generator to be able to retain synchronism, to be able to regain synchronism after the occurrence of a fault. So I think this was discussed in our previous class, and I hope you could understand this. Now, what we have done, I am repeating this because this portion is very important for the understanding of stability. That's why, though I have discussed this in my previous class, I am repeating it here again so that it helps you in understanding the things. Okay. Now, what we have done, you see that now the in the first swing. Why we are talking about the first swing? Because when we have started our course on stability, we have seen that we are assuming that the system is very simple. We have a synchronous machine connected to an infinite bus. There is no other oscillation in this system. So, if the generator becomes stable, or if the generator can regain synchronous speed at the first swing, we can ensure that the synchronous speed or the stability of the system will be maintained. And we are using this logic, we are using this philosophy. So we are observing only the first swing, second, third, fourth swings, these will be there, but we are we want to know whether the system will be able to remain in synchronism after the occurrence of the fault and removal of it. Okay, this is what we are attempting to do. So you see that here the first swing is completed here, means first before the first swing has when the first swing is completed, you see that the rotor position delta 2, it is much ahead of this angle here. What is this angle? This is the input power line and this is the output power curve. So this angle delta here, obviously it is equal to pi minus delta 0. So this angle delta 2 is much smaller than pi minus delta 0. Why we are talking about pi minus delta 0? Because unless the synchronous speed is restored before this point is or at this point is arrived at, the system or generator will not be able to maintain, maintain synchronism, will not be able to regain synchronous speed. Why? To understand that, we have considered this one, this figure diagram. You see here, the same power angle curve we have drawn again. This is the power input line, and we have assumed that we have delayed the opening of the circuit breaker by a small time, by a certain time. We have delayed the operation, we delayed the opening of the circuit breaker in such a way that area A3 and area A4, these are available obviously, and A3 and A4 are such that A4 is obtained, this area A4 which is equal to area A3, it is obtained just at this point when delta 2 becomes equal to pi minus delta 0. Why I am doing this? Because we want to see what happens if the clear opening of the circuit breaker is delayed in such a way that the at this point delta equal to pi minus delta 0, the synchronous speed is just regained. Then what happens? Then you see that this area A3 becomes equal to area A4. Here the speed is synchronous, here also the speed is synchronous, means synchronous speed will be obtained here. But what happens at this point? So long you see that output is greater than input. So here the synchronous speed is regained, but obviously it will not be the operating point because output is still was above the input, output was greater than input, there was deceleration. So the deceleration will be continued, and as a result, speed of generator will become smaller than synchronous speed. As the speed becomes smaller than synchronous speed, what happens? Now again, delta or the rotor starts swinging in the backward direction because delta is now decreasing. So rotor or the delta will become smaller. It will follow this. It will trace the same power angle curve in the reverse direction. Okay, in the reverse direction it will move. That means the first swing is completed and then the second swing has been started. We shall not be observing the second swing. We shall not be discussing about the second swing because it will be rather difficult to discuss from this diagram. We have to draw it again in a separate manner. Okay, but we are assuming that if the generator becomes stable and the first swing, it will be stable in the subsequent swing as well. This is our assumption, and under this assumption, we can say that generator will become stable. Now assume that we have delayed the opening of the circuit breaker by a larger time. Okay, some still delaying the opening of the circuit breaker. That means H3 now becomes somewhat more than this value. If it is increased by a very small value, then what will happen? A3 has increased. So as a result, when this point will be reached, obviously A4 will not be equal to A3. A4 is still lesser than or smaller than A3. If A4 is smaller than A3, then what will happen? Synchronous speed will not be obtained here. Here the speed will be still above synchronous. As the speed is still above synchronous, delta will increase and it will cross this point. But as soon as this point is crossed, what is happening? This is the power input line, this is the power output curve, and this point is crossed with delta with speed above synchronous. As the speed is above synchronous, you see that now delta will go on increasing again. Delta will increase further. As delta is increasing further, what happens? Input becomes greater than output, speed becomes above synchronous, so it becomes more than synchronous. It was already more than synchronous, now it is increasing further. Okay, so it indicates that here the speed was not synchronous, it was above synchronous, and at this point is crossed, input power becomes more than output power. As a result, speed will become higher. It was already synchronous, above synchronous, it will become still higher. As it is becoming still higher, delta will go on increasing. And there is a case or there is a situation when delta will no longer be decreasing again, and situation will be like this. Situation will be like this second case. Okay, delta will go on increasing continuously. There is no reduction in the value of delta because speed was not synchronous and speed could not become less than synchronous. If the speed could become less than synchronous, then only delta could decrease. Here, speed is always above synchronous. As a result, delta is continuing to increase. And this situation, like this case 2, is now happening here. We are getting a situation where this situation like case 2 is happening. So it indicates that the opening of the circuit breaker, okay, opening of the circuit breaker has to be completed at or before this point is reached, and this point is indicated by this angle delta CR, delta critical. Why we are saying this angle to be critical? Because this is a very important angle. If you miss this point, okay, if the circuit breaker is not opened before this point is reached, then the synchronism of the system cannot be maintained, stability of the system will be lost. That's why it is called the critical angle, or it is called the critical clearing angle. That means as if we have applied a fault and we have to clear the fault, and fault must be cleared before the this critical angle is reached. That's why it's called the critical fault clearing angle, or sometimes called the critical clearing angle. Okay, so we have here actually discussed an artificial situation as if an artificial fault has been applied, but in reality, in actual system, this type of situation may happen. A fault may occur here, and there will be circuit breaker at this end and at this end of the line. Circuit breakers generally are connected at the both ends of the transmission line. So, once that circuit breaker will actually open by receiving a signal from the relay. Relay we identified that a fault has occurred, and then the relay will send the signal after identifying it. Will send the signal to the circuit breaker. Circuit breaker in response will open the contact of its contact. Will open its contact. Okay. So the transmission line actually will be disconnected. This will be the situation. Okay. Now here we are not going in that details for the time being. We are dealing with this situation. Okay. When a line generator is connected to infinite bus through a transmission line, and we are observing what happens when the circuit breaker is connected to create a fault and it is open to disconnect the fault. Okay, and we can observe that, we can see that unless the fault is cleared, unless the short circuit is cleared before this point is reached, the system will not be able to maintain synchronism. System will not be able to regain synchronous speed. That means the stability of the system will be lost. That's why this angle is called the critical clearing angle. And how we are actually ascertaining the stability of the system? By observing the equality of two areas. By ensuring that two areas are becoming equal. What are these areas? One area A3 and another area is A4. A3 is power energy inserted into the generator. F represents the energy extracted from the generator. Extracted from the generator means from the rotor of the generator. Here A1, it is the energy input to the rotor of the generator. A2 is the area representing the energy extracted from the or removed from the rotor of the generator. Okay, so energy input, and which energy? It is the extra energy. At this angle delta zero, generator was rotating at synchronous speed because it was a stable situation. Okay, at angle delta zero, generator was rotating at synchronous speed. So kinetic energy corresponding to that synchronous speed was stored at the rotor of the generator. Now, any energy input is extra to that with respect to that energy. That's why this is an extra energy that has given as input to the rotor of the generator. That extra energy has to be extracted. And if we can extract the same amount of energy from the rotor, then again, obviously, the energy content here will be equal to the stored kinetic energy of the generator. And obviously, in that case, here the speed will be above. Speed will be again the synchronous speed. Okay. So if two such areas are available, okay, before this point is reached, then we can say that the system or the generator will be able to maintain synchronism, maintain uh, uh, stability. Okay, here we have created a situation such that this area F4 is actually completed just at this angle delta 2, where after this position is crossed, again input becomes more than the output power and speed become again above synchronous. Okay, here at this point speed is again the synchronous speed, and as the speed is again the synchronous speed, you can say that just moment after this point is reached, again the speed will become less than synchronous because generator was retarding at this point so long up to this in this period. So again the speed will be below synchronous. So as the speed is below synchronous, generator will now move backward. Delta will decrease. So this indicates that the second swing has started. Okay. So by observing the first swing and by applying the equilibrium criterion, we can say whether the system will be stable or not. Okay. And we see that for obtaining or retaining the synchronous speed or regaining the synchronous speed, two such areas must be available, where in one area we are having an energy which is responsible for the acceleration of the generator rotor, and another area which is responsible for the retardation of the generator rotor. And these two areas must be same. That's why the name given is the equal area criterion. So is it clear to every one of you? Could you understand? I have discussed
Yes,
this.
sir.
Now you could understand this. Now let us uh, write mathematical condition to represent this situation. Okay. Now let us start from here. What is this? This the you see that this is the power angle. This is the swing equation. Swing equation means this equation. We have written m d2 delta dt2 equal to pi minus pe. M is the angular momentum. Delta is the power angle. Angle between E and B is the internal voltage or generated voltage. and V is the terminal voltage. Pi is the power input to the rotor of the generator from turbine. P is the power output from the generator, electromechanical, sorry, electrical power output from the generator. Okay, and difference obviously the accelerating power. When P is positive, generator will accelerate. When P is negative, generator will decelerate. So M d2 delta dt2 equal to Pa. This is the swing equation. This is called swing equation. Let us rewrite this equation here. Write this equation here. d2 delta dt2 equal to 1 upon m Pm minus Pe. Pm is the mechanical power input. This was Pi previously written. Now it is a Pm. Pm minus P. Mechanical power input, electrical power output. Okay. Now let us integrate to find out the delta value. Let us integrate. So for integration, let us multiply both sides by 2 d delta dt. So it is 2 d delta dt, okay, d2 delta dt2 equal to 2 by m pm minus p d delta dt, okay, 2 by m pm minus p d delta dt, or it is equal to 2 by m pm minus p means the accelerating power pa d delta dt. Now you integrate what you obtain at d2 delta dt2, it is equal to 2 by m integration delta 0 to delta, okay, pa d delta, okay, it is pa d delta. So now what is d delta dt? You see that d delta dt is nothing but uh, d delta dt is change in rate of change of angle, okay, that is speed above synchronous or below synchronous. Okay, now what happens here? The speed is synchronous. D delta dt at this point is 0. Here again the speed is synchronous. D delta dt is at this, just at this point is 0. Here it is 0. D delta dt is 0. Here also d delta dt is 0. So d delta dt is equal to 0. It indicates that a generator rotor is having a speed equal to the synchronous speed. Or you can say that d delta dt equal to 0, we can say this is the condition for maintaining stability of the generator. So we can say that 2 by m integration PID delta, okay, this we can say this is equal to 0, okay, because the delta dt equal to 0. Okay. So here what is PID delta 0? PID delta equal to 0. How can I write it? It is delta 0 to delta. PA means PM minus PE. P, what is PE? P electrical means peak of the power angle curve into sine delta. P maximum sine delta. So let us know P maximum sine delta. Electrical power output means the delta has a definite value. So P maximum sine delta at the operating point, this is PE. Okay. Or from it is delta 0 to delta. This is obviously where this delta will be where the speed is synchronous again. So it is from delta 0, is considered it is not 0, it is delta 0. Delta 0 to delta 1, say Pm minus P maximum sine delta. Okay, plus delta 1 to delta 2. Actually, we are separating this into two sections. One is from delta 0 to delta 1 and another from delta 1 to delta 2. What are these two sections? Delta 0 to delta 1, delta 1 to delta 2. So from delta 0 to delta 1, electrical power output is 0 here, or electrical power output is this one, power input is this one. Okay. So power input minus power output, because the generator is accelerating here. So from delta 0 to delta 1, it is input power minus output power. From delta 1 to delta 2, it is output power minus input power. Okay. So let us write this. So from delta 0 to delta 1, Pm minus P maximum sine delta, d delta, plus, because this from delta 0 to final delta, well, okay, it is delta 1 to delta 2, it is Pm minus P maximum sine delta, d delta, okay, between these two angles. Obviously, the value will be different depending upon the value of delta. Okay. So here, now you see what happens. Delta 0 to delta 1, Pm minus P maximum sine delta d delta, and delta 1 to delta 2. What is this? It is P maximum sine delta minus Pm, because it was like this. So P maximum, okay, P maximum sin delta because output is more than input. This will be equal and minus sign was, that's why it has been shifted to the other side. Okay, so this is the condition. So this represents area A1 where the generator is accelerating, speed is increasing. This represents the decelerating area where output becomes more than input. Okay, so we shall not, let us not consider this thing because this we shall not go here. So from here to here, this represents area A1 from delta 0 to delta 1, power in mechanical power input minus electrical power output. We are integrating this area between these two, power input minus power output. You integrate this with, this represents accelerating area. From here to here, it is power output and it is power input. We are integrating between delta 1 and delta 2. And these two areas, we see that the condition will be such that these two areas are equal. So for maintaining synchronism, this is the accelerating area must be equal to available decelerating area. Okay, so if two such areas are available, you can say that generator will be able to retain synchronism or retain stable operation. And if such areas are not available in the system, then it will not be possible for the generator to maintain synchronism. Okay, so this is called the equal area criterion. So by applying this equal area criterion, we can actually assess whether after a disturbance, whether after a fault, the generator will be able to maintain synchronous operation or maintain stability of the system or not. Okay, obviously, this requires that we are having a generator connected to an infinite bus. There are no, as if there are no other machines. Why there are no other machines? Because we are ignoring any other presence of any other oscillation in the system. That's why we can apply this equilibrium criterion because we are depending upon the first swing of the generator only. First swing of the generator will be able to determine stability of the generator or not if and only if there are no other oscillations available in the system. If there are other oscillations prevailing in the system, then what will happen? The generator may not be able to retain synchronism, though the first swing shows that the generator is able to maintain synchronism. But in the subsequent swing, because of the interaction between the oscillation of this generator with the other oscillations present in the system, the generator may finally lose synchronism. So we want that no such oscillations are available in the system. And this is possible if the generator is connected to another generator. Okay, that means it is possible if the system is a two-machine system. How this is a two-machine system we are considering? We are considering that our generator is connected to infinite bus. So infinite bus means the total power system. The total power system is now being represented by a very large generator. That is called the infinite bus. Okay, so infinite bus basically is representing a very large generator with infinite capacity. And if this is the situation, then we can say that there will be no other oscillations present in the system, and under that condition only equal area criterion will be applicable. So equal area criterion is applicable under a very simplified condition when there is a single generator connected to large power system or generator connected to infinite bus. Or you can say that this equilibrium criterion is applicable to a two-machine system only. When one machine is the machine whose stability we are considering, the other machine is the machine representing the total power system. Okay. So if we can assume that only two such generators are available in the system, then obviously there will not be any other oscillations present in the system. Therefore, those, since other oscillations are not available in the system, then we can actually decide whether the system is stable or not after observing the first swing only. And equilibrium criterion helps us in taking any decision regarding stability or not by observing the first swing only. So we assume that no other oscillations are actually present in the system. Only oscillation is the uh, oscillation of the generator, incoming generator with respect to infinite mass. Okay, and from the first swing of these oscillations, we are deciding whether the stability will be obtained or stability will be maintained or not. So, equilibrium criterion, you see that it will not be a practical method for determining the stability of the power system, because in a power system there will be many generators connected, large number of generators connected, and all these generators combined together will not be able to act as an infinite bus, because infinite bus is a theoretical concept, but still this equilibrium criterion helps us in understanding the problem of stability. That's why it is very, very important to understand this equilibrium criterion, because it will help you in explaining, in understanding the stability problem. Okay, that's why we are actually studying this equilibrium criterion. Though in determining the stability of a generator connected in a large power system, you cannot apply this. You have to go for the solution of the swing equation by using numerical technique. But that solution of the swing equation using numerical technique will not help you in understanding the stability problem. Rather, by or from equilibrium criterion, actually you can understand the stability problem in a better way, because you can visualize whether with respect to the remaining part of the system your generator is, whether your generator is able to maintain synchronism or not. Okay, that's why equilibrium criterion is being studied here, and we shall be applying this equilibrium criterion only to a situation when only there are two generators, of which one generator is the incoming generator whose stability we are studying. Other generator is the large power system represented as a single generator. Okay, or that we call that single generator as the infinite bus. Okay, so is it clear to you or not? So basically, uh, the criterion should be understood, or should be, you can say that, clear from this explanation. And what we have done later on, we have actually put the equation representing this curve, representing the power input. We have actually represented those things, and finally shown that these two areas may be represented by these expressions. This is one area representing the acceleration of the generator, representing the energy responsible for acceleration of the generator, and this is another area representing the energy responsible for the retardation of the generator. And energy available for acceleration must be equal to the energy available for deceleration. That means energy input to the generator or external input to the generator must be extracted from it if the synchronous speed has to be regained. This is what the equilibrium criterion tells us. And we know this. Obviously, we know before solving this, we also know that for retaining synchronism or for regaining synchronous speed, obviously the stored energy must be the rated stored energy. And rated stored energy is the energy corresponding to the synchronous speed of the generator. Okay. So this is regarding the equilibrium criterion. Now let us apply this to a small example that will help us in a better way to understand the stability problem. Okay. So let us consider a very small problem now. It will help us to understand the equilibrium criterion further. Let us consider this problem a loss-free alternator. Loss-free alternator means we are obviously we have ignored all losses. Here also we shall be ignoring all losses. Loss-free alternator supplies 50 megawatt to an infinite bus. So case is simple. A generator connected to infinite bus. The capacity this generator here is supplying 50 megawatt. The steady state stability limit of its system being 100 megawatt. Now you have to understand this line. What is being stated here? the steady state stability limit of its system being 100 megawatt of the system, actually not its system, the system being 100 megawatt. Determine whether the alternator will remain in synchronism if the prime mover input is abruptly increased by 30 megawatt. Okay, so what does it mean? Can you say it is given that loss free generator, it is supplying 50 megawatt to infinite bus. Okay, 50 megawatt is being supplied to the power system. Okay. Now, steady state stability of the system is 100 megawatt. What does it tell us? What information you can get from here? That the steady state stability limit of this system is 100 megawatt. Can you anybody suggest what does it mean that the steady state stability limit of the system is 100 megawatt? What does it mean?
Maximum power which it can be supplied.
Okay, because actually we can between the we have a generator connected to internet. So we can draw a power angle curve for this generator. What will be the shape of the power angle curve? Obviously, the sinusoidal curve like this, in the sine curve, and we are assuming that we have a cylindrical rotor generator, and if that means we are neglecting saliency. If saliency is neglected, peak of the power angle curve will occur at 90 degree, and at 90 degree, this is the steady state stability limit. And what is this limit? It is equal to 100 megawatt. Means at 90 degree, the value of the power. Okay, that means the power angle curve, peak of the power angle curve occurs at 90 degree, and here it is the steady state stability limit. And what is the value? It is 100 megawatt. That means peak is 100 megawatt, generator is supplying 50 megawatt. Okay, so if the peak is 100, it is given now from this statement, and it is supplying 50 megawatt. So you can find out what is the initial operating angle. Obviously, it is 30 degree sine delta. Okay, sine 30 is zero point 0.5. So it is 50 megawatt, peak is 100 megawatt. So it is 30 degree initial operating angle delta 0. Okay, now what is done? There is not a fault. The prime mover input is abruptly increased. Suddenly, you have increased the prime mover input. Determine whether the alternator is will remain in synchronism if the prime mover input is abruptly increased by 30 megawatt. It was 50 megawatt, it is abruptly increased to 80 megawatt. So if it is increased to 80 megawatt, so power input line becomes this one. 80 megawatt becomes the power input line. So if this is the power input line, the input power line or increased power input line and power output curve, this is the power output curve, they actually are crossing here. So we can find out this angle here. They are crossing here. That means that does mean can you tell me what is the implication of this angle here? What should be this angle? This was the initial operating, this is the input power line, and this is the initial operating angle. Why this is the initial operating angle? Input power line and output power curve. It was supplying 50 megawatts. So this was the operating point. Alright. When it was supplying 50 megawatt, obviously power output point was this one. Input power line is this, power output point is this. It is 30 degrees the operating angle delta zero. Now power input is abruptly increased by 30 megawatt. It becomes 80 megawatt. So when it is 80 megawatt, now what will the generator will do now? Suddenly, power input becomes 80 megawatt. So input becomes more than output. So what a generator will do? It is still supplying this 50 megawatt. It is operating here, but input power goes here. So input becomes more than output. Since input becomes more than output, obviously the generator cannot immediately increase its power output. It is still supplying 50 megawatt because delta cannot actually delta remains at 50 megawatt because for changing the value of delta, why I am talking about changing the value of delta? Because if you want to extract more power from the generator, or if the generator has to deliver more power, its power angle must increase. Okay, EF Vt by x sine delta. If delta increases, then only the power output will increase. But power output cannot increase immediately. Why? Because delta cannot increase immediately. Why? Because for increasing the value of delta, speed of the generator has to be increased. So generator speed will increase and then gradually delta will increase. So what happens? Because the input is more than output, speed will increase. As speed increases, output will follow this curve, this power angle curve. So this becomes power output, this becomes power output. Here at B also this becomes power output. So what happens from A to B? From A to B you see that input power is more than output power. That means always the speed is above synchronous here because generator accelerates, speed increases, so speed becomes above synchronous. Alright, so here input power, output power they are matching. But this cannot be the operating point. Why it cannot be the operating point? Because still the speed is above synchronous. Since the speed is above synchronous and there was acceleration, so obviously rotor will cross this point, it will come here. Delta will increase further. As delta is increasing further, because speed is above synchronous, delta will increase further. As speed is above synchronous and delta increases here, you see that output now becomes more than input. So as output becomes more than input, now the generator decelerates. Because it is giving delivering more power. Where from it will be delivering more power? It will get from its stored kinetic energy. That means speed will decrease, but speed will decrease from the increased value. And increased value is above synchronous. So here speed is decreasing, but it is still above synchronous. So since it is still above synchronous, obviously delta will go on increasing further. It will go on increasing further. Okay, and as it is reducing, the speed is being reduced from after this point, sometime here it will so happen that that speed will again become synchronous speed. When the speed will again become synchronous is when this area, this area AGBA, this area becomes, or an area equal to AGBA. This area is obtained here. So maybe this area is obtained somewhere here, say BM, say here it is GB, like this. Somewhere here, again the area equal to this area will be obtained, and there the speed will become synchronous. So after that, what will happen? The speed is synchronous here, but after that, again the speed will decrease because still the power output was more than power input. As power output was more than power input, then the speed will decrease, as speed will become less than synchronous, and the second swing will start. So this will happen. This will go on. Okay, as this is just 1 minute, this will go on. You can say that the first swing is completed, and the perhaps the if we have to calculate if this thing happens, then the synchronism will be lost. Now let us see whether it is happening or not. So now you see that for our case 50 megawatt is equal to 100 peak value sine delta 1. So what is delta 1? Delta 1 is say 0.523 radian or 30 degrees. So say this is delta 1. Okay, initial operating angle. Now here let us find this angle B. At this point, what is area? Here it is 80 is the input power. Output power curve is 100 sine delta 2 say. So you can find out delta 2, it is 53.2 degree. That means here this angle will be 53.2 degree or 0.927 radian will be the value of delta here. Okay. From delta 1 to delta 2, there was acceleration. So you can area calculate this area. After that, there will be deceleration. So where this area will be obtained, you can determine. Okay. So now you calculate ABG, this area. AB, uh, that is not area ABG. Basically, this is okay. ABG, AGBA or ABG, whatever may be. You calculate this area. What is this area? You see that here 80 minus 100 sine delta. Why 80 minus sine delta? 80 is the input power, increase input minus 100 sine delta is the output power. So integrate, you will get this area. So it will be delta 1 to delta 2. You know the value of delta 1 and delta 2. Put the value. So integrate and put the value. You will get 5.72 megawatt radian. That means the this area is given to be 5.72 megawatt radian. Now you calculate where the same area will be obtained here. Same area will be obtained here. Or since you have to ascertain whether stability will be maintained or not, let us find out this total area. How to find out this total area? This area we know it is 57 point something. So this point we know it is pi minus 57 point that angle. Okay, pi minus delta 2 is this angle. So if you calculate this total area and if you see that this total area is either equal to this area or greater than this area, then obviously the stability will be maintained, because at this point or before that point stability will be, or synchronous speed will be regained. If this area is more than this area, obviously stable synchronous speed will be obtained before this point is reached. If this area becomes just equal to this area, then stable synchronous speed will be regained here. So let us calculate this area from delta 1 to delta 2. This was this thing. Then 100 sine delta minus delta, it is say pi minus, not it is delta 3, it is not delta 2, it is pi minus delta 2. Okay, so delta 2 to pi minus delta 2. Okay, delta 2 to pi minus delta 2, you integrate this, that is 17 megawatt radian. That means this total area is 17 megawatt radian. It indicates that this area is much larger than this area. It indicates that obviously the synchronous speed will be regained much before this point is reached. Somewhere here maybe the synchronous point is reached. So we can say that stability of the system is will be maintained. Why the stability of the system will be maintained? Because the synchronous speed is regained much before this point, and it is regained when output is still greater than input. That means just after that there will be deceleration, so speed will decrease below synchronous. Okay, so delta will decrease. That's why you can see that stability will be obtained. Okay, so the 17 megawatt radian is the available decelerating area, and it is much above that the accelerating area we have calculated. The synchronism will be obtained from the first swing. We can say this. Okay, now there is another part. Okay, now let us see whether, let us find out the stable, it will be stable and maximum permissible limit of prime mover input. So if it is stable, let us now find how much we can increase the input power. It, by increasing the input power to 80 megawatt or by increasing the input power by 30 megawatt, stability was maintained. We could maintain stability by increasing this much of output. But how much we can increase? What is the limit of power increase? Let us find out this. What is the limit of increase in input power? Okay, if you want to find that, say limit of increase in input power is somewhere here. That is not equal to 80 megawatt. So it is somewhere, say at this point, not 89, above 80, somewhere here. And say that angle again, it is delta 1, and somewhere here is the angle will be delta 2. We want to find how much will be the limit of the increase in the input power. How we can find it out? Obviously, for that limit, the synchronous speed will be obtained or synchronous speed will be restored when this input power line and output power curve, they are meeting at this point and at this point, and at this point, just at this point, the synchronous speed will be restored. Okay, so synchronous speed will be regained when just this point is reached. If this is true, then only we can say this is the limit in the increase in the input power. Okay, so for that, uh, let us say delta is representing that angle. So from P1 minus 100 sine delta d delta. Okay, this is the uh, accelerating area, say, and it is equal to delta d2. That means we say that p1 is the limit up to which the power input can be increased. So p1 minus the input minus output integration between delta 1 and delta 2. From delta 2 to pi minus delta 2. Why pi minus delta 2? Because input power line will meet the output power line curve at these 2 points. At the rightmost point, we are having pi minus delta 2. There, it is sine delta minus p1. So this area must be equal to this area. So you now solve this and you will have this equation. From this equation, now you can find out the value of uh, delta 2. Okay, so you see that it is 86.6. So now I am actually I have shown you this thing. You now think this about this thing, and we shall be explaining this. We shall be continuing this portion in our next class. So have I delivered this or have I mailed this uh, PPT to you before? I cannot remember. Have I mailed this already to you? This PPT is available to you already or not? Have I mailed it already?
I don't think so, sir.
No, it was not done. Huh?
I don't
So
think
I
so, sir.
shall, okay, I shall be sending this. So you will be, you try to understand this part, and I shall again discuss this portion because I could not discuss this portion today because it is already 4:30. I shall have to join the other class. Okay, so I shall be mail this to you. You go through this part. You try to understand this. We shall be discussing from this point in our next class. Okay, thank you.
Okay, sir. Thank you.
Okay, now
Thank you, sir.
Anirudh Anand,
Yes, sir.
Arijit Pal,
Yes, sir.
Dipten Mardi,
Yes, sir.
Hasibur Rahman, Manas Patra,
Yes, sir.
Mohammad Kaif,
Yes, sir.
Shreyas Khatri,
Yes, sir.
Saurabh Burman,
Yes, sir.
Shubhadeep Bera,
Yes, sir.
Swapnil Kishku.
Yes, sir.
Anybody who could not respond previously?
Sir, Hasibur Rahman.
Hasibur Rahman. Okay, you are present. Okay,
Yes, sir.
thank you.
Yes, sir.